Okay, deep ocean circulation. There's the right program. There we go. What is going on to make circulation happen in the deep ocean? As we noted, wind blowing up on the surface tends to get our currents going up there, but due to friction, things get weaker and weaker as we go deep. What's going to move things down in the deep ocean? Major factors there are the thermohaline circulation. Therm, temperature, halo, salt, differences in density. Okay, and what were our big factors affecting density of seawater? Again, salinity and temperature. Up at the surface, there's variation there. Evaporation or high levels of precipitation can make our water either fresher or saltier. And we've got weather making parts of the ocean surface either hotter or cooler. So no surprise to have variation there. How's that then going to be impacting the deep ocean? Making sea ice. This is very important in affecting the temperature and salinity of an area of the ocean. Temperature near sea ice, it's ice. What do you think? Yeah, it's kind of obvious there. Cold. Salinity, again, as we have seawater freezing, that's water freezing. Salt doesn't fit into that nice crystal structure, and so gets left behind. And so the non-frozen water around our sea ice is saltier. It's cold, it's salty, it's dense. No, that's not how it's left behind. As we noted before, most of the ocean is deep water. So relatively cold compared to the average for the surface, and very uniform in properties. Where could we get cold water? Well, it's cold near the poles. What leads to there being such uniform properties of this seawater? The diagram highlights this. Range in temperature for the ocean as a whole ranges from around 30 degrees Celsius at the warmest to a little below zero in the coldest areas. Salinity ranges from a low around 33 to a high around 37 for any significant part of the open oceans. So 99% of the total seawater falls within this light blue blobby range. About 3/4 of it all is in this cold and somewhat medium salinity here between 0 and 5 degrees and 34 to 35 parts per thousand. This fits with currents seeking down from near the poles and then continuing to carry water around throughout the oceans. Once water isn't near the atmosphere, things aren't changing a whole lot down there. And so there's not a whole lot that's going to change the salinity or the temperature of that deep water. There's a little bit of warmth coming from the interior of the Earth. After all, that is powering plate tectonics. So over time, that deep water does warm up a little bit. Also, if we have some place that has extra salty water, that can get dense and sink down. Even if it's not too cold, the extra salt can make that happen. And then that will tend to mix in with the deep ocean as well. So we can recognize different major water masses in the ocean. The central waters refer to the shallow waters in the middle of the ocean. This includes our surface and pit decline zones that we talked about before. And then we have intermediate waters, which are somewhat colder, denser underneath that, and deep and bottom waters that are the typically quite cold waters down in the deepest parts of the ocean, below about 2 kilometers. As the diagrams to the right show, we have some different patterns of waters in different oceans. The two little bits circled in red are warmer but very salty water. The rest is coming from near the poles, and being extra cold there, it sinks down. What's the pattern of water flow in the deep ocean? Typically, we have some place at the surface where we have made extra dense water. Maybe there's lots of evaporation, it gets extra salty, a lot of cooling, or perhaps making sea ice, which promotes cold and salty. And this raises the water density until it's dense enough that it will tend to sink down relative to nearby water. Once it's deep down, it can travel around, and there are generally deep ocean connections between all the major oceans. So that connection allows that deep water to travel throughout, be very uniform throughout the oceans. Under modern conditions, the key spot for kind of starting this all out, where the water is first sinking, is in the very far North Atlantic region. So we'll look a little more at that. Present day, it has changed multiple times in the geologic past. Not surprisingly, deep ocean flow, it's way down in the ocean, it's dark down there. Not all that well understood. The number of boats moving around observing surface currents is quite large. Number of extreme deep submarines, much smaller. So there's a lot of details, things that we don't know precisely how they work. For example, been maybe 6 or 10 years back, saw a news item where a relatively fast deep ocean current had been discovered off the coast of Australia. That's quite unusual, but there it was. Okay, so let's start with the sinking. The areas in this kind of greenish bluish color are major areas of sinking water globally, and the far North Atlantic region there around and north of Iceland is especially important for this. Water there sinks down, travels deep under the ocean, from the Atlantic into the Indian and Pacific, before finally getting back up to the surface and traveling around once more. The main direction of flow is towards the equator. Well, if you start at the poles, there's a limit to how far you can go the other way. And of course, also got land in the way, preventing much east-west variation. Surface water, as we get into the mid and tropical latitudes, is noticeably warmer than that deep water. But again, close to the poles, it's getting cold, and ice and or evaporation, not so much evaporation happening there. There's a little bit, but not lots typically, but places that are close to the equator may have lots of evaporation, and that water can move near the poles and get cold as well. Once that water gets denser than surrounding water, it will tend to sink. Sinks as far as it can before it balances out with surrounding density, and then it will flow along from there. Very slowly, we get some mixing, some heating from the Earth's interior, and eventually it comes back up. The Atlantic is the most complicated in its layering. We have the central water, those superficial parts again, and then intermediate, deep, and bottom waters. Lots of layers here. Okay, what's going on? Well, it turns out the North Atlantic tends to be extra salty as well as cold, being near the poles. And that's what sets it up to be a key point of origin for sinking water. Why would it be extra salty? And we have the Caribbean, warm, sunny area, typically. Warm and sunny sets up a lot of evaporation, which is what can power a hurricane. But also, notice those clouds from Mitch here. A number of these are extending well over into Central America. Rain from evaporation in the Caribbean, and an appreciable amount of that ends up going to the Pacific. So the Caribbean is getting somewhat more salty due to the evaporation. Eastern Pacific, somewhat fresher. These storms can be quite devastating. Okay, so we've got the Caribbean contributing to extra salty. Also, across the Atlantic, we've got the Mediterranean. And it's typically warm and sunny there, a lot of evaporation, not a huge amount of river input. The Nile's the longest river in the world, but before it makes it to the Mediterranean, it goes clear across the Sahara. So by the time it comes out at the Delta of Alexandria, even without all the water that we're taking away for irrigation, it's not dumping a huge volume of water into the Mediterranean and diluting it. Likewise, there are various rivers along southern Europe, but nothing too big there. So the Mediterranean water tends to be pretty salty, Caribbean water relatively salty. As that is carried north by the Gulf Stream, it also ends up getting cold, and cold plus salty sinks. That cold, salty water sinking, that's the NADW, North Atlantic deep water here. MIW, that's our salty Mediterranean water coming in. And so this flows down south under the shallower stuff, gets down towards Antarctica. It's even colder there. So that water gets chilled and sinks down once more to form this Antarctic deep water, Antarctic bottom water. Pacific is somewhat less complicated. We basically just have one intermediate and one deep set of colder water underneath the surface. One to the north, I'm sorry, over here to the right is the north, one to the south, both intermediate and deep levels. Pacific's kind of the end of the line for the deep circulation, so it tends to be somewhat slower circulation. Indian Ocean's even simpler. We only got one pole to be concerned about. North Pole isn't affecting the Indian Ocean. Asia's in the way. So we have this deep water. Again, it's the stuff that started out in the far North Atlantic, got near Antarctica, cooled once more, sunk under intermediate, and then we have the surface waters, and here's some extra salty water coming out of the Red Sea. What about the Arctic? Arctic Ocean is on the fresh side compared to typical for oceans. Opposite situation for the Mediterranean. It's cool, often not much evaporation going on. And it's got a lot of big rivers going into it. Things like the Yukon, Belina, across Canada, Alaska, Siberia, and the like. It's largely surrounded by land masses, so doesn't mix all that much out with the other oceans. And of course, cold, often there's ice, not nearly as much studied as several other areas. So not so well known, the properties of the deep Arctic. Okay, so that's our pattern out in the big main oceans. What goes on in a smaller sea, an enclosed area along the edge of the ocean? Varying degrees of isolation may be present. With all that land around, they are much more influenced by the local characteristics of the land, of the climate, as opposed to out in a big open ocean where there's mixing of water from different parts and you get greater averaging out. So you get different patterns. For example, the Mediterranean, already mentioned, relatively enclosed, relatively warm and sunny, and so it has rather warm and salty water in it. Water flows in at the surface from the Atlantic. As we get more evaporation moving in, it gets saltier. It sinks down towards the east in the Mediterranean, and that deeper, dense, salty water travels underneath and flows out once more into the Atlantic, where it contributes to the extra salty, deeper water sinking down in the far north. You'll notice we have currents flowing in and out depending on how deep you are. This is something that can be taken advantage of by a submarine if it wants to try to sneak into the Mediterranean without making lots of noise with its motor. It can simply ride shallow current in. If it's trying to sneak out, riding the deep current out will be an option there. Very different pattern is found in the Black Sea. The Black Sea actually connects to the Mediterranean, but it is further north. Instead of having the Sahara Desert along one of the shores, the Black Sea has primarily cool, moist areas of Eastern Europe around it, and a little bit of Asia there. So plenty of water, not as much evaporation. You have some major rivers like the Danube flowing in. And so the surface water of the Black Sea is on the fresh side. As you go deeper down, water is saltier, but also there's no deep water connection between the Black Sea and the Mediterranean or any other water body. And so that deep water in the Black Sea is trapped and gets stagnant. So we have temperature. There is a thermocline in the summer, not much difference in the winter. And there is a permanent halocline. Fresher at the surface, saltier deeper down. And so as we go down, we go from a relatively high level of oxygen down to essentially 0. And then we have anoxic water, no oxygen deeper down. We need oxygen. Of course, we can't breathe it when it's dissolved in lots of water, but ocean animals characteristically need oxygen as well. Down in the anoxic zone, it's largely just bacteria. Well, and archaea, if you're being precise in your divisions there. The diagram also shows that we have increasing levels of hydrogen sulfide as we get down low to no oxygen. Hydrogen sulfide will react with oxygen. That's why you don't get much of the two together. Hydrogen sulfide is perhaps most famous, or maybe infamous, as the smell of rotten eggs. Okay, why do we think of hydrogen sulfide as smelling bad? Well, it's pretty toxic, and so you don't want to be standing around sniffing something that's toxic to you. Ooh, this stinks. You're not going to just keep on breathing it. Ironically, in very small amounts, hydrogen sulfide actually is used in the body, essential for some functions, but large quantities, trying to breathe the stuff, not only does it stink, it will poison you pretty readily. On the other hand, you do have bacteria that happily use it as an energy source. So only those organisms that can tolerate anoxic conditions, and also cool and dark and all that stuff, can live deep in the Black Sea. Water flowing in currents deep under the ocean, we can't see it, but just like any other water flow, it will have similar types of properties. It can flow over things just as a river up on land can flow over a waterfall. Oceanographers like to claim that the biggest waterfall in the world is under the ocean along the Denmark Strait between Greenland and Iceland, along there. That's where we have the cold, dense water that sank down in the far North Atlantic, going over a more shallow underwater ridge. And as it goes down the other side of the ridge, we have tumbling around, just as you have when a river flows over a hill and tumbles down in a waterfall beyond. And then it goes along and fills in the deepest parts of the ocean beyond. Similarly, that cold water moving north from Antarctica, the coldest stuff makes it over a couple of ridges and then eventually doesn't make it over the next one. A little bit warmer than that, and makes it over the first, next, but not over beyond that. And so we get tumbling, mixing going on. Now, of course, water on top versus air. Water is denser, so there will be difference in the details of what this tumbling and flowing looks like compared to a waterfall on the surface. But the same basic principles are applying to both of these. As I briefly mentioned before, long term we see changes in these. Circulation patterns have been different going back into the geologic past. Continents in different places. Do we have glaciers? That pretty obviously affects where we're going to have extra cold water. What are the global climate patterns? If it's hot overall, then we may not have some place where water gets cold and tends to sink, and instead it may be warm, salty water that's doing the sinking. So a variety of changes there. What could change relatively quickly? Well, if you watch your fingernail, plate movement is pretty slow. Long term it's important, but doesn't change real fast. Glaciers, likewise, tend to take a while to grow and shrink. Climate change, at least with human help, can happen somewhat more rapidly and potentially be a fast enough change to be a problem for some living things to keep up. Here's a view of the Arctic Ocean. Again, currently Our global pattern of deep circulation is driven by cold, salty water that's sinking up here in the far North Atlantic. What's going to change if we have global warming going on? Well, it's kind of obviously getting warmer, but also with that warmth, we'll tend to see more water vapor in the air and thus potentially more rain and snow flowing through these big rivers into the Arctic. Also, we can get more melting of snow and ice. Some of that's going to be flowing into the Arctic along here as well. So warmer, more melting, more precipitation. All that means that the Arctic is going to tend to be warmer and fresher. Back from the first lab, trying to get your layers of water. Warmer and fresher water, both of those do not sink as readily as cold and salty. We're seeing changes happening. Already, the flow in the North Atlantic is noticeably slower than it was in older records of the region. What's going to happen long term? If we are no longer seeing the sinking of cool, salty water there that starts up the global pattern, now it's going to have some impacts. Now, exactly how this will work, hard to tell, but trying to run an experiment on the Earth, not such a great plan. What do we do if the experiment goes wrong? We don't have someplace else to go. So we're continuing to change something as big as the global scale pattern of deep ocean currents. What effects will that have? Probably some of them will be bad. Okay, so a quick review on ocean current patterns. Key factors that create ocean currents are the force of winds and differences in density between different places. The direction that a current takes is strongly influenced by the rotation of the Earth as well. Here in the northern hemisphere, winds and currents will tend to end up going off to the right relative to what we'd expect due to Earth spin. The southern hemisphere will be left. If we have currents coming together, that brings in extra water. Should get a little bit of a bulge, and that will give more pressure, water tending to sink there. Currents moving apart, diverging. That's less water, less pressure. We'll get a bit of a depression, and deep water tends to rise there. In the deep oceans, cold, salty water sinking towards the poles, especially in the far North Atlantic, is the key starting point for that pattern of water movement through the oceans. Okay, so that's a run through on the currents.